So the plan for today is to study the dynamics of systems of two equations. So we will have systems of linear autonomous differential equations with two unknown functions. So the matrix A will be of size 2. And we will see how the phase portrait is dependent on the eigenvalues of this matrix A. So what we know from last time is that the solutions are dependent on the eigenvalues and eigenvectors of the matrix A. And today we will see different phase portraits depending on the signs of the eigenvalues. So signs of the eigenvalues have great impact on the solution. And we'll see different pictures of the solutions. So this will be the first thing. Then the second thing will be to study differential equations of order n. We already know how to translate them to first order systems of differential equations, but we will also see another method where we can compute the characteristic of equation of this differential equation and work out solution out of this characteristic equation. And we will also see how to solve non-autonomous systems. So we'll solve non-homogeneous differential equations. So where the non-homogeneous part won't be zero. We already know for first order differential equation. So we know that we can just use guessing. This is one way. The other way is to use variation of constants. And today we will generalize this to higher order equations. And if time allows, we'll start to study vibrating systems. So we will study vibrating systems. This means that we will have second order differential equation, and we'll study what's the impact if we impose some force on this motion. We will have 3 or 4 cases, and some of them will be worked out today and some of them next time. And this will be also the last thing in our course. And then we will start preparing for your written exam. Okay, and let's start. So today's title is the dynamics of systems of two DEs. Our system is x1 dot is equal to a11 x1 plus a12 x2, and then x2 dot is a21 x1 plus a22 x2. So it's autonomous system. So here a11, a12, a21, and a22 are real numbers. As we said, it's convenient to introduce this matrix A, the matrix of coefficients. That's why they have indices 1, 1, 1, 2, 2, 1, 2, 2. Otherwise, we could have A1, A2, A2, A3, A4. But to be more consistent with this matrix notation, we use double indices. So 1, 1, and 1, 2, then A2, 1, and A2, 2. So this is our matrix. And let's assume that determinant is non-zero. Otherwise, we don't have two solutions, then otherwise we have only one solution. So let's assume that determinant of A is non-zero. And lambda 1 and lambda 2 are eigenvalues of A. So from last time, we know that the solution to this differential, to this system, which I will write for future reference with star. So from last time, we know that the solution to this system star is a linear combination of this form. Xt is equal to, and then we have some constant C1 times e to the power of lambda 1 t times eigenvector V1 plus C2 times e to the power of lambda 2t times V2. So V1 and V1, V2 are eigenvectors of A. And let us also assume that we assume that lambda 1 is not equal to lambda 2. So this is really the proper solution. If lambda 1 was lambda 2, then we would need to use Jordan form and generalized eigenvectors for the general solution of this system. But let's assume, for simplicity, that lambda 1 is not equal to lambda 2. And now we have a few cases depending on the eigenvalues lambda 1 and lambda 2. So case 1 is that both are real. So lambda 1 and lambda 2 are both real. We know that if they are not real, then they are complex conjugate. We will deal with this case later on. So we start with the case where both are real. And let's say that the first subcase will be that both are of the same sign. So subcase 1. Let's say that both are positive. And we order them in the increasing order. So lambda 1 is smaller than lambda 2, and both are positive. This will be our solution which we are going to observe. So this is a general solution, a family of solutions, which means that C1 and C2 are parameters. We have to vary C1 and C2. So, and it's easy to extract first solution to these two solutions out of this equation. So which two? The two one where C1 or C2 is equal to 0. So if C1 is 0, then the solution is x of xt is C2 times e to the power of lambda 2t times V2. So this is in fact, this solution is in fact in the direction of this eigenvector V2. So this solution is in fact a so-called degenerate solution because it's a line. It doesn't change its shape, it's a line. So this the part which changes is only e to the power of lambda 2t. So as t varies, this part changes, but it only means that we are changing the size, the length of this vector V2, which means that we are all the time we are on the line. And let's say that our line is that one. So if this is V2, then we are on this line all the time. So this is one curve in the family of curves which solve this equation. And then the same is true if we take C2 equals to 0. So in this case, x of t is C1 times e to the power of lambda 1t times V1. Again, this is a so-called degenerate solution. It's a line. Now, before I write the line in the so-called phase plane, so we call this image, this picture, we called it a phase plane, the phase plane. So we are just drawing the solution x of t. where the one axis is first coordinate function, and then the second axis represents the second coordinate function, so x1 and x2. And note that here we don't have any dependence of time on time, so it's autonomous system. So before I write it, let's think about, I fixed v2. Where should I write? Is this v1 arbitrary? Can I write it in any direction? So I will write a few possible directions. So here or here. We know that v1 and v2 are linearly independent. So the only condition is that v1 doesn't lie on the line, on the red line. So v1 could be any of those. These are the, for example, candidates for v1, but only one is correct. Does anybody see which one is correct? So now I'm still working in general. I don't have, if I would compute, if I would work with real data, I would compute v2, v1, and then there wouldn't be any doubt where to write this v1. But now I'm working in general. I've chosen a general v2, and I claim that v1 is now already determined. Yes, so this is the solution in the chat. Jure says that they need to be orthogonal. This follows from linear algebra. So if you have a matrix A, then the eigenvectors are orthogonal. So if you have a symmetric matrix, then the eigenvectors are orthogonal. So this is V1. In the symmetric case, I forgot to say that A is symmetric. So if A is not symmetric, then any other option is also okay. But in the symmetric case, I had the symmetric case in mind. Of course, this completely changes the problem. So in the symmetric case of A, V1 is completely determined. Otherwise, not necessarily. Otherwise, it could be any of those in any of those black directions. So this is then V1. Okay, these are two degenerate lines, and then we have to determine different combinations. So if you combine C1 and C2, which are non-zero, then we get different solutions. And let's say that, so let's say now that C1 and C2 are not zero. Then of course we cannot know what happens for specific t, but we can at least look what happens for in the limit when t goes to minus infinity, when t goes to zero, and when t goes to plus infinity. So let's see what happens when t goes to infinity at first. What is happening with this solution? So this is limit when t goes to infinity of this expression C1 times e to the power of lambda 1 t v1 plus C2 times e to the power of lambda 2 t v2. Now, when t goes to infinity, so v1 and v2 have fixed length, let's say 1, but it doesn't matter, and C1 and C2 are fixed constants, so they don't matter. So in the infinity, those two parts have to be, those two real numbers have to be compared. And since lambda 2 is bigger than lambda 1, we see that this part prevails. So in the infinity, e lambda 2t is much bigger than e to the lambda 1t. So e to the power of lambda 1t is negligible compared to e to the power of lambda 2t. Because if we compute, if we multiply both with e to the power of lambda 2t minus lambda 2t, we get On the left-hand side, we get 1, while on the right-hand side, we get e to the power of lambda 1 minus lambda 2 t. And you see this lambda 1 minus lambda 2, this is now smaller than 0 because lambda 2 is bigger than lambda 1. And as t goes to infinity, this exponent goes to minus infinity. So as t goes to infinity, this exponent goes to minus infinity, and e to the power of minus infinity is 0. So everything goes to e to minus infinity goes to 0. That's why we see that this e to the power of lambda 2t prevails in the infinity, which means that in the infinity, our solution behaves like C2 times e to the power of lambda 2t times V2. So it will either, depending on C2, we will either be here or here. So if C2 is smaller than 0, if we fixed V2 to be to point in this direction, then C2, if C2 is smaller than 0, then it will be pointing in the opposite direction. So we will be here, t is minus infinity, or here. So we don't know yet. And if C2 is bigger than 0, then we will be here or here. So C2 bigger than 0 and C2 smaller than 0. So this is one case. And then to see the behavior of our curves, we will also compute the limit when t goes to minus infinity of x of t. Now I won't rewrite everything again, but if we observe the brackets above, what we see when t goes to minus infinity, then this part where lambda 2t will be negligible compared to lambda 1t because it will be much more negative. So lambda 2 is bigger than lambda 1, so lambda 2 times t will be more negative than lambda 1t, and so this will disappear, this part will disappear, because lambda 2t will be minus infinity, and it will fall much quicker than lambda 1t. This means that when t goes to minus infinity, the solution will behave like C1 times e to the power of lambda 1t times V2 times V1, sorry. So this means that we will be either here. We have to look at, so we'll be somewhere along this orange line. But we have to see what's the length of our vector. So we will be pointing along orange line. Okay, I just wanted to to draw blue line here, but I have to think a little bit. So C1 times e to the power of lambda 1t, as t goes to minus infinity. So since lambda 1 is positive, lambda 1t will go to minus infinity. So this will in fact be very small. So this will go to 0. So the length will go to 0, which means that we will really point in the direction of this vector v1, but the length will be 0, which means that we will be somewhere here. So either here or here or here or here, depending on the sign of C1. So as t goes to minus infinity, we'll be going toward 0, toward the origin, but along, so the slope will show the slope will point in the direction of the orange line, so in the direction of V1. So this means that if we try to draw an example, we have 4 possibilities. If we start here, our solutions will be, I will use another color, which I haven't used before. Let's say this one. So our solutions will be like that, and then like that, depending on the size of C1 and C2, and then like that, and like that, and so on. So the curves, which will look something like that. This will be one phase portrait. And I can also write directions. So we start from minus infinity. We are in the minus infinity, we are coming closer to the origin. The slope is in the direction of orange line, and we are then going out and nearing in the asymptote. Our asymptote will be the other eigenvector, so the red line, and the same for the other 4 possibilities. So we have 4 possibilities because we have 4 combinations of signs of C1 and C2. So C1 can be plus or minus, and C2 can be plus and minus. So we have 4 combinations, and it tells us in which of these quadrants we are. So this is one possible phase portrait. And let's look at an example where, so we'll have an example where the matrix A will have 2 real eigenvalues, both will be positive. So example. X1 prime is equal to 3x1 plus x2, and then x2 prime is equal to x1 plus 3x2. Our matrix A is 3, 1, 1, 3. So I put 3 and 1 in the first row, and then 1 and 3 in the second row. So we could, it's easy to compute the eigenvalues and eigenvectors in this case, but why not use computers since we're already at mathematical modeling? So we can use Mathematica. Mathematica is good for symbolic computation. So this is example I've already computed. So we have here our matrix A is 3, 1, and the second row is 1, 3. And there is a function which is already built in Mathematica eigenvalues. And then we put in the matrix. Note that the notation is a little bit different than MATLAB, but for symbolic computation, it's better to use Mathematica. And then eigenvectors of this matrix, there is also a function. So we get 4, 2. For the eigenvalues, they're really both positive, real, and the eigenvectors are 1, 1 and minus 1, 1. So yeah, in this case, we really had a symmetric matrix. That's why we expect eigenvectors which are perpendicular, and they really are. If you compute the dot product of both of them, we get 0. So when we have a symmetric matrix, if we compute one eigenvector, then we can know the other vector without computation. So we just put it to be perpendicular to the first, but only in the case of symmetric matrix. Okay, so I will just write down the solution and then we will draw it in MATLAB. So x of t is, so the eigenvalues were 4 and 2, e to the power of 4, 2, C1, and the eigenvector for the eigenvalue 4 was 1, 1, plus C2 times e to the power of 2t, and then minus 1, 1. So if I just write a phase portrait in this case, and then we will also do it in MATLAB. So we have the one eigenvector is 1, 1. This is, let's say, this one. And then the other is V2. This is the one which is perpendicular to it. This is V2, V1. Now, lambda 2 is bigger. I mean, lambda 1 is bigger, so this 4 is bigger than 2. So what's gonna our phase plane look like? So it will be like that. So we will be nearing, in when t goes to minus infinity, the slope will be we will be going to the origin, and the slope will be this blue one. So it will be like that. And then in the infinity will be, our asymptote will become V1. And then depending on the signs of C1, C2, we get 4 different combinations of these motions, like that, or like that. And then here like that. And in this case, like that. So in this case, the point, the origin is called the source, because those curves are going from the source when times grows, are moving out of this source. So the point 0, 0 is called a source. The origin is a source. Because the curves are moving out of the source as time grows.
So when t is approaching minus infinity, we are approaching the source.
Yes.
Okay, thank you.
So, and let's check also with MATLAB that this phase portrait is really correct. So I have here. I took lean space. I took for the initial interval, I took the interval from -3 to 0.5. This is by trial and error. If I took -10, 10, then we'll see. I can show you then later what happens. And I will explain why. So I was trying which interval is it's best to take to get a phase portrait which makes sense. And then I put C1 and C2 to 1 and just computed x's, the values of x and the values of y. So this is x1 and x2 in our notation. And then I plotted the solution curve with red. And then on the same picture, I plotted the solution where C1 is 1 and C2 is -1, and all the other 2 possibilities as well. So when both are negative and when one is negative and one is positive, with different colors, of course. And then also these degenerate solutions where one of the constant is 0. So those are those 2 lines, V1 and V2. Okay, and let's see our portrait. Yeah, so you see, this is one case, then the other, third, fourth, and then the degenerate cases. Okay, and before we end this first hour, let me only change this. For example, If I try to draw this for t from -3 to already 1, probably makes a problem. Not really. Let's take -3 to 2. Yeah, here you see the solution doesn't look senseful. Why? Because the x coordinate is on the scale between -4000 and 4000. And this is because if you look at the solution, we have here e to the power of 4t. And if I take t, which is in this case 2 or 3, then I have e to 4 times 2, so e to 8, and it's really a big number. So the scale in x-axis really has to be big. That's why in this case it's from -4000 to 4000, but then all the solutions look like different lines. That's why I have to be careful when I choose this initial interval where I'm gonna plot the solution, and for example, taking the upper bound to be 0.5. This exponent 4 times 0.5 will be only 1, and e to the power of 1 will be around 3. So it won't the scale in x-axis won't be too big, and the image is then senseful. So yeah, this is this case, and then you can extrapolate to bigger values, because we are only interested in the actual portrait, not exact solution, but only how the portrait looks like. Okay, this is all for the first hour. Yeah, please ask.
Yes, I mean, in this picture, these lines don't converge to the lines of V1 or V2.
Yeah, let's increase T1. So let's increase T. We have to increase T.
Okay.
Let's say that it's 1. Yeah, yes, it still doesn't converge. So we have to take even bigger T. Yeah, now it doesn't look good. So we have to focus. If we want to get the behavior in the limit, we have to focus only on this part here. So what I'm gonna do, I will draw just this red curve. So I don't want to see the x's which are smaller than 0. So I will only draw this red curve, and for t's which are positive. So let us do this again. So I will copy this. Save as, let's say, base portrait 5 or 1. Save. And I will take only these which are big, 1, 2, let's say 3. Let's see if this makes us better asymptotic behavior. Yeah, now it looks like it's this line. So maybe 1 to 2, so that we'll see that it's really coming close to this line. Yeah, still, if I take 1 to 2, then it already coincides with this line, because our scale is already from 0 to 3000. And yeah, so this is in fact already asymptotic behavior. Maybe 1 to 1.3. Yeah, so yeah, I have to do a really fine analysis to be able to see that it's approaching the proper line. Even for t equals to 1, it already coincides with the line. So maybe I have to change the lower limit a little bit, 0.7. Yeah, so you see, this is already asymptotic behavior, so it coincides with this line, which we want. But to see how it approaches to this, one needs to do more thorough analysis. So I would have to take the interval here, which is really small, for example, 0.5 to 0.52. Maybe this will give us better picture. It's already here. It's aligned. So maybe let's try 0.1 and 0.13. Yeah, not successful. So this shows us that even for small t's, it very rapidly coincides with the line we want.
So in general, this shape of this picture depends only on the sizes of lambda 1, lambda 2. So it just rotates the picture for 90 degrees.
Yes, yes. So it's a linear combination of these two vectors, yeah. So the actual solution is then the linear combination of V1 and V2, and those are coefficients. And we see that since 4, so it's 4 is twice 2, this coefficient very rapidly becomes so this coefficient very rapidly becomes negligible. Maybe it will be better if I increase also C2. If I make C1 smaller than C2, this will be more visible. Yeah. So if I make, let's say C1 is 1, and I will take for C2, I will take 100. And now I expect that our curve won't become line so quick. What I did, 0.3. Now I'll take 1 to 5. Yeah, now it's already too big. So 1 to 1.3. You see, when I take 1 to 1.3, this second curve is still prevails. We are not in the asymptotic behavior yet, because C2 is 100, and still this second part prevails. So we have to increase this right endpoint. Now you see it starts to the first line starts to prevail. Let's put 1 to 2.3. I expect that now the jump will be very quick. Yeah, so here, yeah. So we started here. The first line prevailed, and then we moved to the other line, which became prevalent. So here, if I decrease t, then we would start to come closer to the origin. And then as t grows, then the other curve starts to prevail. And this is then the asymptotic behavior. Okay, you see, sometimes it's easier to know general picture than to figure out the solution just by drawing the solution, because it's difficult to know what's the appropriate interval on which we should write the solution. But once we know what kind of solution we expect, then we can just vary the interval to look at the specific part of the solution. So by varying this t, we are in fact analyzing different parts of the solution. So here we got now this part, you see. This is then this part of the solution. And it's very difficult to draw all curves on one picture. We really need to take the proper interval for t. Okay, let's do a break of 15 minutes and continue at 10:35. So we finished the first hour with this example where the solution was a linear combination of the eigenvector with corresponding to the eigenvalue 4 and the eigenvector with the corresponding value eigenvalue 2. Then I tried to show you the asymptotic behavior in MATLAB, and I just couldn't find the interval t, the interval for the time parameter, which would show this behavior well enough. It always looked like we get a line v1, and the explanation was so this can be explained. So I was trying to show you on the example where C1 and C2 are both equal to 1. And all the time intervals looked like we get this V1 as the solution. So we got different parts of this line V1 as the solution. And this can be explained because it seems that we were very close to this orange line. So we were not in fact trying to plot this red curve, which is quite far from the line V1, but we were in fact on one of those solutions which are immediately which immediately become a line V1. So we were in fact very close to V1. That's why this solution was not visible. But when I took C1 equals to 1 and C2 equals to 100, then we in fact got one of those solutions which are far enough from V1 so that the asymptotic behavior becomes more visible, more clear. So this was this picture. So in fact, this curve is one of the curves in this quadrant. Okay, let's continue. So recall that our first case was that both eigenvalues were real and both were positive. And now let's take an example where both of them will be negative. And so subcase 1.2. And so that our picture won't change a lot, let's take that now lambda 2 is smaller than lambda 1. So lambda 2 is bigger than lambda 1 in the absolute value, but both are smaller than 0. Our solution, our general solution is still of this form: C1 times e to the power of lambda 1t v1 plus C2 times e to the power of lambda 2t v2. And again, we would like to analyze the limiting behavior when t goes to infinity and when t goes to minus infinity. In the subcase 1.1, when t went to infinity, this vector v2 was the prevalent direction. However, when both eigenvalues are negative, when t goes to infinity, the direction where the real number, where the coefficient is less negative will prevail. So lambda 1t when t goes to minus infinity, when t goes to infinity, will fall much less rapidly than lambda 2t, because lambda 2 is more negative, and as t goes to infinity, lambda 2t will go to minus infinity, and this will be more rapidly than lambda 1t. So the prevailing direction here will be c1. So this will be not c1 times, but it will be limit as t goes to infinity of c1 times e to the power of lambda 1 t v1. So the direction will be v1. But this real number here, this coefficient, will go to 0. So it will in effect go to origin. So the limit will be 0, 0, the vector 0, 0. So before we had, when t went to infinity, the direction was v2, and the length of the vector was infinite. But here, the direction, the prevailing direction is v1. But in fact, the length goes to 0, so we're in fact reaching the origin. While in the other case, when t goes to minus infinity, the situation will be vice versa. So this part will prevail because lambda 2t will be more positive. Lambda 2 times t will be, so lambda 2 is negative, and then t is negative, so it will be lambda 2 times t will be positive, and in the absolute value, lambda 2t dominates lambda 1t. So c2 times e to the power of lambda 2t v1 is then the dominant direction, and this coefficient really goes to infinity. So above it went to 0, but here it goes to infinity, so it will go to, the direction will be v2, and will be going out of the origin. So on the phase portrait will be in fact the same as the phase portrait above, only the arrows will point in the other direction. So let's draw here v1, and then v2. And then as t goes to minus infinity, we are going out of the origin, and as t goes to infinity, we are in fact going to the origin. So will be like that. So the direction of travel will be in the opposite direction as before. And so on. So like that. And like that. And in this case, the origin will be called the sink. So before it was called the source, because for negative t's, the motion started in the origin and then it went out of the origin. But here the motion starts in the infinity and then it goes to the origin. So this is a sink. Since for big T, we are approaching the origin. Okay, we had two situations. Both lambdas were real. Once they were both of this. In both cases, they were both of the same sign. Only one they were both positive, and in the other case they were both negative. Once we get the source in the origin, and then in the other case we get the sink in the origin. And now the third possibility is that lambda 1 and lambda 2 are of different signs. So subcase 1.3. lambda 1 is negative and lambda 2 is positive. Let's see what happens in this case. Again, we are computing the limit as t goes to infinity of this expression C1 e to lambda 1 t v1 plus C2 times e to lambda 2 t v2. So we have to compare those two coefficients. And what do we notice? So lambda 1 t goes to minus infinity, and C2t, lambda 2t goes to infinity, because here we use that lambda 1 is smaller than 0. Here we use that lambda 2 is bigger than 0, which means that this part is negligible because this part goes to 0, 0. So this coefficient e to lambda 1 t goes to 0. That's why the whole summand, the first summand goes to the origin, so it becomes negligible, while the other summand goes to the direction v2, and it goes, the length is infinite. So this goes to infinity times v2, because e to lambda 2t becomes infinite. So the asymptote is the line in the direction of v2. And then on the other hand, we compute the limit as t goes to minus infinity of this same expression. Now, e to lambda 1t, so lambda 1t goes to infinity, while lambda 2t goes to minus infinity. So in this case, this second summand becomes negligible, and the first summand points in the direction of v1, and the coefficient is in fact infinity. So here we notice that in both cases, as t is very small or as t is very big, we are far away from the origin. Once we are near the line v1 and in the direction of v1, and in the other case we are in the direction of line pointing with slope v2. So how would the phase portrait look like? Let's take v1 and v2. Let's say that v1 lies on this line and v2 lies on this line. So as t goes to infinity, we are approaching v2. So we are here. And so this is t goes to infinity. And then as t goes to minus infinity, we are approaching v1. So we'll be here. And in between, we have some superposition of the vectors v1 and v2, and the coefficients are exponential functions. So it turns out that the picture is something like that. The motion is something like that. So the curves in the family of solutions are some kind of hyperbolas. They're not hyperbolas, but they resemble hyperbolas. And the same is true for the other quadrants. So the motion is in this direction. So t from minus infinity, from the red line to the blue one. So from red to blue. And in this case, as one would expect, the origin is called a saddle. So the origin is called a saddle. Okay, and one numerical example. So we need a matrix A which has real eigenvalues of different signs. It turns out that one possible choice is 1, -3, -3, 1. So our system is x1 prime is x1 minus 3x2, and then x2 prime is -3x1 plus x2. I will again use Mathematica to compute the eigenvalues and eigenvectors. So this is example 2. And you see the eigenvalues are 4, -2. They're really of different signs. And the corresponding eigenvectors are -1, 1, 1, 1. So I'll just, for convenience, write what are the eigenvalue and eigenvector pairs. So lambda 1 is 4, v1 is 1 minus 1, and then lambda 2 is -2, and then v2 is 1, 1. And let's see what is the phase portrait. So we expect phase portrait of this form. Let's see if this is indeed the case. So this is the example. So again, I chose C1 and C2 1, 1, and then 1, -1, -1, -1. So I took all 4 possible combination of signs for the coefficients, and this is our solution to differential equation. So the eigenvalues are 4 and -2. And let's run the example. See, and what we get is really the phase portrait we expect. So 2 degenerate solutions, yellow and black, and then those curves which go from yellow to black curve in the asymptote. So once t is negative and once t is positive. And the origin is really a saddle point.
What were the eigenvectors again?
So for 4, it was 1, -1, and for -2, it was 1, 1.
Thank you.
Okay, and there are 2 interesting cases, 2 interesting phase portraits remaining for the cases where the eigenvalues are complex conjugate. So we have now subcase 2. Now we have subcase 2. And so in the subcase 2, no subcase, case 2, and then we have 2 subcases. We have case 2. Lambda 1 and lambda 2 are complex conjugates, so alpha plus minus I beta. So alpha beta are here real numbers. And beta is non-zero. So if beta was 0, then we would be then we would have both eigenvalues which are real and in the same, but we won't study this case. So we have beta is non-zero, and now we separate 2 cases according to alpha being 0 or non-zero. let's first take that alpha is non-zero. Alpha is non-zero. So the solution is still, the solution to our differential to the system is still x of t is c1 times e to alpha lambda 1 t times v times u plus c2 times e to lambda 2t times w. But as we did last time, we saw that we can rewrite this as a linear combination of two real solutions by taking the real part of x and the imaginary part of x. And when we take the real part, we get one real solution. And then when we take the imaginary part, we get another real solution. And then we can form linear combinations of those two solutions. So real part of x of t and imaginary part of x of t form also solutions. And then x of t can be written as c1 times real part of x of t plus c2 times real times imaginary part of x of t, and c1 and c2 are allowed to be complex. And as c1 and c2 go over all complex numbers, then all solutions are described. So for different choices of c1 and c2, we get all solutions of this form. So this is really another way of expressing the family of curves which solve our equation. And why would we like to express this in this form? Because we will draw a phase portrait in the real plane. That's why we need the real part of x and imaginary part of x. And then we will draw the phase portrait only for C1, C2 being real. Phase portrait will be drawn only for real C1 and C2. Okay. So I can write down then this form from last time. So C2 was e to alpha t. This was the real coefficient times, and then we had this real and imaginary part, and they were C1 times cosine beta t plus minus C sine of beta t. This is what we did last time, so I'm just rewriting the result, and then plus C2 times, and then we had sine beta t plus cosine beta t. And of course, a vector is missing, so here we have vector u, and here we have vector w. These are real eigenvectors, so u is here. It turned out, okay, let me write this like u1 and then u2, because it turns out that u is u1 plus I u2, and then w is just u1 minus I u2. Because so last time we saw that if lambda 1 is a eigenvalue with the eigenvector u, then lambda 2 is complex conjugate of lambda 1, and w is also complex conjugate of u. That's why I have here real part of u and imaginary part of u, and w is then just the complex, just the conjugate of this. Okay, now we have to draw the phase portrait of those solutions x of t. Okay, let's. It will be difficult to analyze this form of the solution, so we will still use the complex form. So I will here still write the complex form. So it's e to alpha t. So alpha plus So let's look above. So C1, it's C1 times e to alpha plus IT plus I beta t u, and then plus C2 times e to lambda alpha plus I minus I beta t times W. Okay, and what I'm gonna do now is, so it is e to lambda t, and then I have here C1 times e to I beta t u, and then plus C2 times e to minus I beta t w. Okay, and what I'm gonna do here,
Isn't it without this because it's in the front?
sorry, without which one?
T. Inside brackets.
Inside brackets, yeah. Where is the?
No,
Where
it's-
shouldn't this
it's
stand?
without, so because it's already in the front, so e to the power of alpha t.
But this lambda 1 is multiplied by t. So I just plugged in for lambda 1, I plugged in alpha plus I beta. So this t must be multiplied by both summands. So t is multiplied by alpha and also with I beta.
Okay, I see. Thank you.
Okay. So this is this one. Okay, this is a general solution. And let's try to draw a forced phase portrait for this. So let's take C1 and C2 wants to be equal to 1. What we get is e to alpha t. So this is real, no problem with this. And here we get e to I beta t u, and then plus e to minus I beta t w. Okay, and this is just this e to alpha t, and then we have e to I beta t u plus this is e to I beta t w conjugated and everything conjugated. So I just this conjugation, I use this conjugation to get rid of I, and since I will then conjugate also W, I have to conjugate it again so that nothing changes. Okay, and now I will try to draw this. So let's also use that this W prime, so this U is U1 plus I U2. This W is then U1 minus I U2. So then W prime is U1 plus I U2. Okay, so this W prime is in fact equal to U. Okay, so I will draw U. Let's say that this is U. Then W prime is also U. Then W prime is this vector here. And beta is a fixed real number and t varies. So as t varies, what's happening with this so what's happening with this part? So we have e to I beta tu. As t varies, this part, so the absolute value of this coefficient is always 1, because it's e to I and then something real. So in fact, we are only rotating the vector u in the, so we are only rotating the vector u around origin. So this e to I beta tu, it's only a rotation around the origin. So we are traveling along a circle. So of course I didn't draw a nice circle. I will a little bit correct this. So it's a circle with radius the length of u. And then the second vector e to e beta t w prime u, and then everything conjugated, is also traveling along the same circle. So this is also of size 1. And then this is also traveling along the same circle. And then we are just taking some linear combination of two vectors on this circle. So we are still on the circle. So this part in the brackets, this is some vector on some circle, on the circle. And as t varies, we are moving along the circle. So if there wasn't this part e to alpha t, then the curve would be a circle. And for different C1 and C2 we would be on different circles. So the phase portrait would then look like a family of circles with centers in the origin. But now we have to also take into account the impact of this e to alpha t. So what's happening? What is the impact of e to alpha t? So if alpha is bigger than 0, what's happening is as t grows. So if alpha is bigger than 0, then this e to alpha t is in fact increasing function, because exponential function with a positive coefficient is increasing, and it goes to infinity. If alpha is smaller than 0, then what's happening is the opposite behavior. So exponential function is falling. So in fact, we are moving along the circles, but for bigger alphas, we are jumping from a circle to a bigger circle. But if alpha is smaller than 0, we are jumping from bigger circles to smaller circles. And we can also compute the limit. So limit as t goes to infinity of e to alpha t times this expression in brackets, which I'm not gonna write again. So this expression in brackets has constant absolute value, is constant for every t. and this e to alpha t is going to infinity. So we're going to infinity as t goes to infinity, while if t goes to minus infinity, e to alpha t will go to 0, because alpha t will go to infinity. So e to alpha t will go to 0. And so we are going to the origin. On the other side, the motion is opposite. So as t goes to infinity, we'll go to 0. And as t goes to minus infinity, we will go to infinity. So let's draw both possibilities for the phase portraits. So if first alpha is positive, let's say that for t0 we are on some circle, and then this is t0. Let's say that we are on some circle on the x-axis. It doesn't matter. We could also be in some other point of the circle, but here I started with the x-axis, and then we're starting to travel, and we will be jumping from circle to circle. So we'll be going around the origin because of the bracket part, but the radius will increase. So we will in fact spiral out of the origin. So this will be the direction of the motion. While if we go, if we decrease t, so if we send t to minus infinity, we will be still going around the origin, traveling around the origin, but the radius will become smaller and smaller. So we'll spiral towards the origin. And the second picture, the second phase portrait is the same, only that we have to change the direction of the arrows, because t and minus t, I mean, infinity and minus infinity have now opposite meanings. So now we are going in this direction towards the origin. Okay, and the case where alpha is 0. So here, if alpha is 0, this was subcase 2.1. If alpha is 0, this is also seen from the discussion above. So subcase 2.2. If alpha was 0, then the phase portrait would be the union of circles with centers in the origin. So then this would be closed curves. So above, the curve is only is not closed. However, in this case, the curve is closed. The curves are all closed, and they are in fact circles. And the motion is in one of the directions, either in this direction or in the opposite, depending on C1 and C2. Okay, let's look for the end of this hour, and for this discussion of phase portraits, let's look two examples. So in the first example, we would like that alpha is not 0. So we will take, for the matrix, we take the matrix -3, 2, and -1, -1. So it's clear already from the determinant that, it would be clear from the determinant of A minus lambda identity that the eigenvalues are complex conjugate. So this is our A, then our system is -3x1 plus 2x2, and then x2 prime is -x1 minus x2. Let's compute the eigenvector eigenvalue pairs. This is this example 3. And you see that the eigenvalues are -2 plus identity, and the corresponding eigenvector is 1 minus identity 1. So the other pair is just the complex conjugate of the first pair. So lambda 1 in this case is -2 plus identity, and V1 is, let's look, is 1 minus identity 1. Not 1 minus I1. And then lambda 2 is just the complex conjugate pair. So it's -2 minus I, and V2 is V1 conjugate. So it's 1 plus I1. So we see here that what is alpha and what are alpha and beta. So lambda 1 is e to lambda 1 is, so no, not lambda 1, but e to lambda 1t is e to -2 plus I t. So it's e to -2t, and times e to it. So alpha is -2 and beta is 1. So we expect the spiral behavior, and we'll go from the infinity into the origin. Okay, and let's do a simulation in MATLAB. This is this case, so you see alpha is -2, beta is 1, and again, I take all different combinations of C1 and C2 and plot the solutions. The solutions are computed in the same way as in the general case. So I just plot those real part times C1 plus the imaginary part times C2. So here only they are a little bit rewritten. So I wrote here as C1 cosine beta t plus C2 times sinus beta t. In fact, the real part would be C1 cosine beta t minus C1 sine beta t. And then the imaginary part would be C2 sine beta t plus C2 cosine beta t. Okay, the form of the solution is just rewritten a little bit. And then let's run this example. And you see, we really get spiral behavior. So these are those different colors. The curves of different colors are different spirals. Maybe it's better. Maybe I can change C1 and C2 to different ratio, and this will be more clear. Let's take C1 to be 1 and C2 to be 10. And in all the other cases, I will also put 1, 10, and 1 minus. So the ratio to 1 to 10. Yeah, here it's becoming more clear. And yeah, this black, so this black example only travels from the origin to some point. If I want to get better part of this curve, I would have to increase the interval for t, but I would have to increase the interval for t only for this curve. So if I increase the interval for t for all the curves, then this green would go from minus infinity to the origin, and the picture wouldn't be clear anymore. So I would have to change the intervals where those curves are defined for each specific curve in this family. So in this specific case, this black curve, I would only need to change in the code. Black one is this one. So let's change here the interval where it's defined to -1, let's say to from let's say -10 to 10. And now, yeah, we only got this one, this black curve. But yeah, you see that if I just change the interval, then I can simply get 2 big range in one direction, and then the picture doesn't become clear anymore. So I didn't change this properly. So let's say -3 to 3. Yeah, now, yeah, we see that now the black one prevails, but now it dominates other curves. So maybe it's better to take -3 to 1. Yeah, still it dominates other curves. So one has to play with those intervals where the solutions are defined. And the last example for where alpha is 0, I will take the differential equation x prime is equal to t. No, x prime is equal to v, and v prime is equal to minus w squared x. So this is because of the implication for motion. X is the position and v is the velocity vector, and v prime is then the acceleration. But so in our notation, it would be x1 prime is x2, and then x2 prime is equal to minus w squared x1. So our matrix is then 0, 1, and then minus w squared 1. And I will take w to be 1 in the example. So our matrix will be, in fact, 0, 1, 1, 1. And this is what I didn't, I don't have calculated. So let's do it now. Example 4, it's A is 0, 1, and then 1, 1. And we would like to compute the eigenvalues and the eigenvectors. So this was not a good choice. It is here -1, of course. -1. That's why, because the eigenvalues were real, so this wasn't a good choice. You see, now it's better. So it says -1, third root of -1, and then this second expression is then its complex conjugate. So it's in this case, what's the eigenvalue? Lambda 1 is third root of unity. And lambda 2 is its complex conjugate. So it's third root of identity conjugated. So it's third root of -1. And the third root of -1 conjugated. This is -1, 1, third root of -1. So these are, you remember from analysis that the roots of the complex numbers, the complex number form a triangle, proper triangle. So I here one of the solutions is -1, -1 to 3 is -1. But the other solutions are then the other two vertices of the proper triangle. So it has to be 60 degrees, so that when I compute its third, when I use the exponent to the 3, I should get -1. So this is one solution and this is the other solution. So this is lambda 1 and then lambda 2. Okay, and let's look at the phase portrait in this example from in MATLAB. And you see, we really get circles. Now here they look like ellipses, but if I change the ratio so that it's real size ratio, then we see that we get that we really get circles. Okay, let's do a 15-minute break and then we continue in 11:40, unless there are some questions regarding what we did this hour.
Yes, I've got a question for case where eigenvalues are real numbers.
Mm-hmm.
So if this matrix A isn't symmetric,
mm-hmm.
then if I understand correctly, the only difference is that these lines on which V1 and V2 lie wouldn't be perpendicular.
Yeah, that's true.
Okay, thank you.
That's true, yeah. Because so how can you formulate examples? So A must be, if A has 2 is of size 2 times 2, then it has and it has 2 real eigenvalues, then we know that it's similar to this diagonal matrix with eigenvalues on the diagonal. And this this P is a similarity matrix. With eigenvalues as columns, eigenvectors as columns. So in fact, what you can do is just choose P to be invertible. If you take P to be invertible, you just take V1 to be a vector of your choice and V2 a vector of your choice. This will be, so then the A computed in this way will give you a phase portrait with V1 and V2 to be two degenerate solutions. So this will be V1, and for V2 you could choose any vector which doesn't lie on V1, so V2. So you could start with this, and then the solutions would be behaving in the same way as if V1 and V2 would be perpendicular.
Okay, thank you.
Okay, let's do a break and meet in a little bit less than 15 minutes. So for the last 20 minutes, we'll look at another possibility to solve one linear differential equation of order n. Now we know that it's possible to translate it to the system and then solve this system of differential equation of first order, and then translate the solutions for the initial differential equation. But there is also one more direct way. So linear DEs of order n So linear DE of order n, this is a linear differential equation with derivatives up to order n present. So xn is equal to some function of t, x derivative up to n minus 1 derivative of x. And let's write this right hand side as a1 of t times an minus 1 t times n minus first derivative of x plus an minus 2 times n minus second derivative of x and so on, plus a1 times x derivative, and then plus a0 t, which is a non-homogeneous part. So n minus 1 first derivative a0 t times x plus some non-homogeneous part f of t. So those AIT are just coefficients, are functions. In the non-homogeneous part, f of t is also a function. As before, a system is homogeneous. I mean, a differential equation is homogeneous if f of t is always equal to 0 and non-homogeneous otherwise. And this differential equation is autonomous if the coefficients are constant, if the functions ai are constant for every t. Now, what we've done so far, we've already said how to translate such a differential equation into a system of differential equations. So we introduce new unknowns. x1 is just x. And then x2 is x1 prime. And so on. xn is xn minus 1 prime. And then xn prime is obtained from our initial equation. So it is an minus 1 of t times xn minus 1 times xn, because so we had here n minus first derivative of x. N minus first derivative of x is in fact xn. So it's xn, and then plus an minus 2 of t xn minus 1 and so on, plus a1 of t x2 plus A0 t times x1 plus this non-homogeneous part. So our system is then, in fact, the system of those differential equations without the first condition, because the first condition is just saying that x will be written as x1. So this, we don't need this condition anymore. So the differential equations are then those n of them. We know how to, we know that the solution of this system is n-parametric. So the vector x of t is then a function of t, and then n parameters, c1 up to cn. So when we vary the parameters c1 up to cn, we get at most, and usually we get n linearly independent solutions. And this will be also translating this back to the original equation. This will get us, this will give us n different solutions to the different functions which solve our initial differential equation of order n. So this gives us n different solutions to the function, to the differential equation star. I will just write it as star. Okay. Let's assume now that we are in the autonomous case, because this is the only case we know how to solve. So we are in the autonomous case. Which means that x and derivative of x is equal to a(n minus 1) times x n minus first derivative plus so on, plus a1 first derivative of x plus a0 x, and we don't have the non-homogeneous part. So when we do the translation to the system, gives us the equation, the matrix, in fact, gives us the matrix A of this form. So the matrix of the system will be of this form. So if we look above, we have the first n minus 1 equation will be just x1 prime is x2. So the first row will be 0, 1, 0, 0, 0. Then the second equation will be x3 is x2 prime. So the second row will be 0, 0, 1, and 0, 0, 0, and so on. So in the first n minus rows, we'll get only zeros, just zeros and only 1, 1 in each row. And this one will be in the first upper diagonal. So this matrix will be 0, 0, and 1s in the first upper diagonal and zeros elsewhere. While in the last row, what we're gonna get in the last row will be, so we just need to look at this differential equation. So we get xn prime is equal to an minus 1 xn. So here we will have n minus 1 minus a plus an minus 1, then an minus 2, then an minus 3, and so on, up to a0. So in the last row, we'll just get those coefficients. And when we are solving system, so the solutions to the systems, the solutions of the system are formed as e to lambda it times vi, where lambda I is the eigenvalue of A, and vi is the eigenvector of A. And now, maybe you recall from linear algebra, probably you did this at linear algebra, but if you didn't, I will just tell you, this is the so-called companion matrix to the polynomial of this form. So A of this form, if we have polynomial P of X, a polynomial P of X is equal to x to n minus an minus 1 x to n minus 1 minus so on minus a1 x minus a0, then forming a matrix A in this form that we get, we put in the first n minus row, we put ones in the upper diagonal, zeros everything in all other places, and then the coefficients in this order in the last row. This is called then A is its companion matrix. And what's the relationship between P and its companion matrix? The relationship is that the zeros of the polynomial P are exactly the eigenvalues of A. So the relationship that the zeros of P are exactly the eigenvalues of A. This is not very difficult to prove. You only need to, so the eigenvalues are obtained by as the zeros of the determinant of A minus lambda identity. And if you try to express determinant of A minus lambda identity, you see that it is a constant multiple of the polynomial P. So it's really an easy check. So you have to do a Gauss elimination on A minus lambda identity, and you will see. So when you do a Gauss elimination, you will get upper triangular form, for example, and you get that the product of the diagonal entries is some multiple of this polynomial P. And this proves that the eigenvalues of A are the zeros of the polynomial P. Which shows, so what can we infer from here? So we would like to solve our differential equation of order n. We know that we can obtain the solution by translation to the system. We know how to solve the system. So the system is solved just by computing the eigenvalues and the eigenvectors. And then out of those eigenvalues, so now I will just write you, so the system, the solution of the system is x of t is then C1 times e to lambda 1t v1 plus C2 times e to lambda 2t v2 plus so on, plus C n times e to nt vn. Okay, but this xt is in fact, what is this xt? This is x1 of t, which is in our case, so I will write this as vector, x2t up to xnt. But what we are interested in only is this first component. When we are solving the differential equation of order n, we introduced this x1 to be, by definition, equal to our x. So in fact, when we are solving this system, we are only interested in this x1. And this x1 of t is equal to C1 times e to lambda 1t. And then v11, let's say v11, where v1 is a vector with the first component v11 and some other components on other places, then plus C2 times e to lambda 2t, and then v2, which is, in our case, it's only the first coordinate of this v2 is of interest to us, and so on, plus Cn e to lambda nt v n1. But these v11, v21 up to vn1 are just constants. They are just some real numbers, so we can just absorb them in C1. And so we don't really bother what those v11, what those first components of the vectors are. So x1t can be expressed as C1 some tilde, some new constant, times e to lambda 1t plus C2 tilde e lambda 2t, so on. So we see that the solution to our system is just, so the solution is now a function. That's why we don't have any vectors involved anymore. And this solution is a linear combination of the functions e to lambda it, where lambda I are the eigenvalues of A, or by what I've said above, are just zeros of the characteristic polynomial of our differential equation. So lambda 1 up to lambda n are zeros of the polynomial p of x, which is formed by replacing, so p of x is formed by replacing the derivatives of our function x with the corresponding powers of x. So I will write this as p of lambda, this p of lambda, so this is lambda to n minus a n minus 1, lambda to n minus 1, and so on, minus a1 lambda minus a0. So this is another way of solving a differential equation of higher order. So we expressed, we know, we used systems to show that every solution of our differential equation of higher order is of this form. And this is the only part where we need systems, because now that we know what's the form of the solution, we see that we only need to determine the zeros of our polynomial. In general, this is a difficult task, but we already know that we already have methods to solve nonlinear equations. So we can use one of the methods to solve nonlinear equations. So a polynomial is a nonlinear equation, and we can use one of the methods to find its zeros. Okay, this is all for today. Next time we will say a little bit more about system, about higher order differential equation, and we'll study vibrating systems. And I think we will finish the material and in 2 weeks we start with preparations for the exam. Are maybe there are some questions regarding today's material? Okay, if not,